Let's now look at some different cases that can happen when we are factoring the denominator when trying to decompose the fraction, and seeing how to handle those cases in terms of integration. So for instance, we've looked at what can happen with distinct linear factors so far. So when we factor, we end up with all linear factors that are distinct from one another. However, there's a chance for us to have all linear factors, but not necessarily distinct linear factors. So for instance, if you look at this particular setup here, I have some linear factor in the denominator, which is ax plus b, and then the same one, which is ax plus b squared, and it can go all the way up to any value n. So to handle that, what we do is we put different factors in the denominator, one with an exponent of 1, the next with an exponent of 2, and then just still simply constants above it. Probably easier to show rather than explain. This formula will probably make more sense if I walk you through the details. So I have the integral of x minus 2 over 2x minus 1 quantity squared times x minus 1. This denominator has already been factored, but as you can see, we have a factor that's repeated, so 2x minus 1 quantity squared, because that's literally the same thing as 2x minus 1 times 2x minus 1, okay? Now, here's how we handle that in terms of our guess, because the next thing that we do in this process is we guess at what the breakdown looks like. So we take our fraction in factored form, and any factor that is on its own, so just linear and on its own, we just treat it as we did before. So I'm just going to go ahead and write a over x minus 1. Now this next term, the 2x minus 1 squared, I write it as a linear first, and then put some constant over that, and then I write it again, but as a quadratic, and a different constant above that. Now, it's sometimes confusing to students as to why you wouldn't make this a linear here, and I'm not going to go through the details as to exactly why that is, but suffice it to say, you can. It's just going to make your process in solving for these coefficients more difficult, and you will always result in finding that c is equal to 0, and you just end up with a single constant up here. So for simplicity, this is the easiest way to do it. Now, if this had been to the third power, we would of course do plus d over 2x minus 1 to the third. This is what's being said here. You just continue writing additional factors until you get to whatever that exponential power is. Now we're going to leave it at 2 because with the quadratic involved, that's going to make the problem a little bit more difficult to solve anyway. So throwing a cubic in will just make it that much more difficult algebraically. Now, in order to solve, the process is still basically the same. The first thing that we want to do is multiply everything through by the factored denominator. All right, so when I multiply the left-hand side of this equation by this factored denominator, I end up with just x minus 2. That whole denominator cancels. Well, a over x minus 1 times this factored denominator would leave me with a times 2x minus 1 quantity squared. b over 2x minus 1 would leave me with, or times this denominator would leave me with b times 2x minus 1 to the first times x minus 1, and then plus c times x minus 1. And we have an equation where we need to solve for the coefficients. Now, the different techniques that I showed you can come into play here. You would always want to start with choosing strategic values of x to simplify things and get the easiest ones first. So for instance, I could let, I could let x equal 1, for instance. That's an easy one. And if I let x equal 1, I would have, let's see, 1 minus 2 is negative 1. And that would be equal to a times 2x minus 1 squared. So this would be 2 minus 1, that's 1. 1 squared is just 1. Okay, so that's just 1. Plus b times 2 times 1 minus 1 is 1. Well, this term actually goes to 0. Okay, that's great. And then this term, c times x minus 1, would go to 0 as well. So those terms both disappear. And very easily, very quickly, I learned that the coefficient a has to be negative 1. Now, if I let x be 1/2, it looks like. It gets a little bit trickier with the fractions, but let's see here. 1/2 minus 2, that would be 1/2 minus 4/2, so negative 3/2. 2 times 1/2 is 1. 1 minus 1 is 0. So this is chosen purposefully to make this term be 0. It would also make this term, make the term with b go to 0. And I would end up with c times 1/2 minus 1, which is negative 1/2. Solving this, I could multiply everything through by negative 2. So that would be c equals positive 6. Well, no, actually it wouldn't, because, sorry, the negatives would cancel, but then also the 2's would cancel. That would be c equals positive 3. Sorry about that if that was confusing. Okay, so now we got a and c solved for. What about b? Problem with b, this term right here. If I was going to cancel out and try and solve for b, one option would be to use 1/2. We've already used that, and that's solved for c. Another option would be 1. Well, we've already used that, and that's solved for a. We don't have any remaining terms to solve for b by just picking strategic values of x. However, we do know some things to start with. We know what a is, and we know what c is. We can take that and use them, and basically plug those into the equation, and just let x be something else. 0 is usually pretty easy. And then, since we know what a and c are, that would just leave us with b. So we just plug in x equals 0, a equals negative 1, c equals 3, and the only variable left is b, and we can solve for it. So if x is 0, this would be negative 2, and then a is negative 1, so then that's times 2 times 0 minus 1. So that's negative 1, but then it's squared, so it becomes positive 1. b, we don't know. But then we have 2 times 0 minus 1, which is negative 1, and then 0 minus 1, which is also negative 1, plus c, we know to be 3, and 0 minus 1 is negative 1. So, like I said, the only variable remaining is b. So let's simplify. So negative 2 equals, negative 1 plus b minus 3. So then if I add 4 to both sides, that would cancel out the negative 1 and the negative 3. And if I add 4 over here, that would give me positive 2. So that shows me the values of all coefficients, so a, b, and c. So that's a viable way of solving for coefficients that you can't get with strategic values of x that will cancel terms out. Just pick anything for x, plug it in, and definitely also plug in things that you already know, and that will often be enough to solve for some remaining variables. If it's not, that's where the method of equated coefficients comes into play and is helpful then. All right, let's see what we have so far. So I now have written this integral as this form right here. So a is -1, so it's going to be -1 over x minus 1 plus b, which is 2 over 2x minus 1 plus c over 2x minus 1 quantity squared dx. Okay, now when we had linear factors that were distinct, then the integration was very straightforward. Any factor that involved a term that was linear in the denominator and a constant in the numerator, we could just use the natural log rule and integrate those very easily. So these first two terms, no big deal. This third term, however, it's a little trickier because it's a square in the denominator and not a linear. So the log rule doesn't apply. But I think actually u substitution does. So it's not that much more difficult, but it's not as easy as the log rule. So we'll just walk through the steps. So the first two terms integrate very easily. It's going to be negative natural log of absolute x minus 1 plus, then this one might get a little bit tricky because the thing is you do have to pay attention to the chain rule if you aren't, if you don't have a multiplier of 1 here. So far, all of our factors, I think, have just had a factor of 1. Here I have a multiplier of 2. So effectively, if I let u equal 2x minus 1, then du would be 2 dx. So it just so happens that the numerator is the derivative of the denominator. We're not going to have 2 times the natural log. We're just going to have the natural log of the absolute value of 2x minus 1. Okay? If you're not sure of exactly why that is, continue to walk through the steps of u substitution here and finish that problem out. But this is what we'll end up with. Now, this last part, I'm going to leave it as an integral and go ahead and factor out the 3. So it'll be 1 over, oh, and actually I'm going to change this to make it 2x minus 1 to the -2nd dx. And the reason for that is, of course, because the power rule could be used here, but not until we've used some u substitution. So 2x minus 1 du would be 2 dx. So I also need a factor of 2, or I could just divide everything through by a half instead. And I think that's what I'll do. All right, so this will become, I gotta write all this out. Give me just 1 second. So plus 3/2 times the integral of u to the -2nd du. All right, now I can actually integrate that. It would be nice if I didn't have to copy these each time. U to the -2nd, we would add 1 to that exponent, so that would be u to the -1 over -1 plus c. And then my final step here, my last time of having to write these, it would be minus, so that's from the negative in the denominator. Then I'm going to put 3 over 2 times the value of u, which was 2x minus 1. And then plus c. So a little bit trickier in terms of integrating, but not that bad. And that's effectively what ends up happening anytime you have the repeated linear factors.